we talked yesterday a little bit about the physical nature of gravitons and the apparent practical impossibility to detect single gravitons, which also led us to reflect on how useful these might be in the end as physical concepts, certainly those that you connect to any kinds of observables. Then, on my way now, I want to talk about the perturbative path integral. We briefly reviewed or contrasted what it means for the very simple case of the quantum mechanics of a non-relativistic particle to quantize it either using canonical methods, that's more the standard way of proceeding, or using a path integral, which is, well, the less standard way, certainly for what you're learning in your first quantum mechanics course, and it might look like a little bit of an overkill in terms of complications, but the benefits do become apparent once you get to relativistic quantum field theories. Now, in principle, these two ways of constructing quantum theories, they are equivalent. I mean, it's not that that one gives you a different result from the other. So, in principle, wherever you can actually complete these quantizations, if you want to think of that as kind of a process, that gives you at least one quantum theory associated with a classical system, then certainly they should do the same job, and that can be very explicitly seen for this example of the non-relativistic particle. So on the one hand, you can just go and solve it canonically, then you have the quantum Hamiltonian, and you just you try to diagonalize it and to find its eigenvalues and eigenstates. The eigenvalues being the energies of the various states the system can be in. Alternatively, you can try to compute the propagator of the theory, which contains exactly the same dynamical information. And for that, as I told you yesterday, you have a path integral representation. Now, these two complementary things of going about the quantum theory exist also for field theories. And the essential distinction is kind of what is, as one says, manifestly kind of invariant in one description as opposed to the other. So when you come to a canonical picture, then unitarity tends to be manifest. So that just means, unitarity just means I have a unitary time evolution, and that's just obvious if you write it at least to the I, h hat t, and h being a self-adjoint Hamiltonian operator. Then immediately you can. It's obvious that this is you're dealing with unitary theory. On the other hand, in a Hamiltonian formulation, Lorentz covariance, a manifest Lorentz covariance, is broken, because when you're talking about having a Hamiltonian evolution, you have already made a choice of time, which is kind of the variable conjugate to the Hamiltonian, to the energy. And if you have chosen a specific time, then you're just referring, in principle, to a given Lorentz frame. Okay? And to show then that the physics is equivalent, if you go to some other Lorentz frame, well, you can do that, but it's more work to do it. So that, and it's not manifest. It's not just by staring at the formalism that you see, well, obviously, this is the physics behind this is covariant. Now, this is different when you go to the path integral. There, you just work with e to the I times the action. And of course, the action is exactly built just from tensorial quantities, so that you have, it is a Lorentz scalar. And therefore, it's kind of totally blatantly obvious, as one says, it's manifest that what you're doing there is Lorentz invariant or Lorentz covariant. On the other hand, in this formalism, to show, say, that something is unitary is then more work. Okay, so it exhibits or it makes obvious certain inherent properties of the theory, and they are more obvious in one formulation than in the other. And very often in quantum field theory, you are very keen on keeping invariances or covariances manifest. That holds not only for Lorentz or Poincare invariance, but also for gauge invariance when you come to talk about gauge field theories. And it turns out all of these things are neatly and kind of accommodated in a path integral formalism. And as a whole way, we set up a perturbation theory, with associated Feynman diagrammatic expansion that works very nicely in a path integral formulation. And this is why this is so overwhelmingly popular in quantum field theory. But in principle, you can also do it as a canonical way. And what this entails for gravity, of course, we'll see as we go on. What I wanted to say, I want to briefly comment here at this stage about general relativity. Of course, the full theory is not Lorentz invariant. I mean, because it's Lorentz invariance, as we've seen, is tied to a fixed background, which is Minkowski space. So this invariance is certainly there when you talk about gravity perturbatively, where you're just thinking of these linear excitations on this fixed background, but not there in general, because GR exactly describes general curved space-times, and those don't have no global Lorentz invariance of any kind. But to some extent, the role of the invariance group in that case is played by a much, much larger group, which is the group of diffeomorphisms that has come up this week already. So the freedom to make arbitrary choices of coordinates to describe your physical geometry in. And also there you have an issue of, do you want to work in a formalism which makes this, the invariance under space-time diffeomorphisms manifest? Then you better choose again for a covariant kind of path integral formulation. If for whatever other reasons you prefer to do it the canonical way, then that will involve kind of a 3+1 splitting of the space-time. And that will exactly kind of break manifest diffeomorphism invariance. That doesn't mean it's no longer there, but it doesn't stare you in the face as much as it does when you choose a covariant formulation. So in a way, things are a little similar. So even when it comes to full gravity. Okay, let us now turn to where we ended yesterday. Write down the path integral, and this time we write it down not for the particle, but straight away for gravity. So Z is a symbol often used to denote a path integral, and you can make it depends on various things. So it depends on the boundary conditions you impose, and they're often suppressed as a notation. Be careful in given applications what the implicit boundary conditions chosen are. What they also depend on are the parameters that appear in the action of the theory. And if I now refer, say, to the Einstein-Hilbert action for gravity, and I let it have a cosmological constant term for generality, then it would depend on the Newton constant and this cosmological constant, the path integral. So let me just keep this dependence explicitly here. So this is my path integral. Now what does it depend on? Here we had the path dx for the particle case, and already yesterday in my discussion at the end, I said, well, what really should be here are four-dimensional geometries. So four-dimensional geometries are, of course, objects g mu nu of x and t. So one of these g mu nus, that's again a functional integral, where kind of one point in the space I'm integrating over is a full configuration g mu nu over my space-time or piece of space-time, depending on what I'm where I'm what the domain of my path integral is. So let me denote the space of all geometries of the four-dimensional manifold M by this calligraphic G. Now, what is usually meant by here is not the metrics themselves, because as we saw, they carry gauge freedom. There is redundancy in the elements of the metric, but what one really wants to integrate over here are physically distinct configurations. And that usually is indicated by this notation with square brackets. And what an object G mu nu with square brackets means is an equivalence class of metrics under the action of the symmetry group, the group of diffeomorphisms that still acts in a non-trivial way on the G mu nus. So this just indicates, that we have already kind of quotiented out by this freedom, and we are sitting on a space where you integrate over each inequivalent geometry exactly once. So that's the idea of the path integral. Yes? Yeah. To start with, I'm only considering a single given manifold M. Okay. And what the status is of a possible sum over topology you may want to add here. Well, we may come back to that point at some later stage. So what you have to do, as usual, you have to take the integral over all these configurations with respect to some measure, which I haven't specified here really in detail, what this is supposed to be. And then each of the geometries you weigh with a phase factor that is e to the I classical action. And in our case, this is just the Einstein-Hilbert action of G mu nu. And of course, this only depends on the geometry. If I move here G mu nu by diffeomorphism, it gives, of course, exactly the same action. So in that sense, the way I've written it here should maybe kind of manifest that this is indeed an object that's invariant under four-dimensional diffeomorphisms. Now, we'll get back to this object in its full generality later. It's very ill-defined to start with, because it's of course, an infinite dimensional, it's a functional integral, and you have to worry also about this, how to get rid, actually, of this gauge dependence here. There are many, many, many problems to address before that can become kind of a well-defined expression of any kind. Now, currently, we're still working with a linearized theory. So we ask ourselves a simpler question, which is to say, if I now make the approximation that I just work with linearized fields, I'm working, I'm doing perturbation theory around Minkowski space. That is just a space on which that theory is defined. And then I might then try to systematically take into account higher orders, higher than quadratic orders that appear as perturbations to kind of the lowest order theory. Then I'm in the setting of usual relativistic perturbative quantum field theory. So let's just see for the remainder of the lecture today where that takes us, taking this kind of approach. So this would be the perturbative path integral for gravity, usually called. And what you do, you split S into kind of a free theory plus interaction terms. So as usual, free theory will mean the one that is just quadratic in the dynamical variables. So we can easily do the path integral because all path integrals will be Gaussian integrals, which we can do also quantum field theoretically. And then I systematically, order by order in perturbation theory, I will take interaction terms which are of higher order into account. So that's what the split means. Yes?
Regarding the Z of alpha and Gn,
yeah.
That the U's are two complex equations with a given alpha and a given Gn?
No, not at all. Of course, what you're doing in the path integral, you're not summing over classical solutions, but you're summing over all configurations, subject to certain boundary conditions.
So what is the alpha and Gn correspond to?
Well, it just corresponds to the parameter that appears in the action.
Okay.
You see, I take, like for the particle, I take a path and I evaluate its action, but it will then also, for example, depend on the mass of the particle. But the paths themselves, of course, have a priori absolutely nothing to do with classical solutions. So that's also a point that is important to recall. So that's what the path integral does. You're taking a quantum superposition of all objects of a certain kind. They can also be very, very far from classicality in general. And just the superposition of those gives you the quantum theory. And if you're lucky, you can then express the quantum theory in certain regions of parameter space as being well approximated, say, by classical trajectories. Yeah, but I mean, the beauty of the path integral is that these things you're summing over there or integrating over there, well, they have nothing to do, or very little to do with any classical solutions of that same theory. Okay, so you make this split, and then, well, just like you do in bosonic, fermionic, standard quantum field theories, you make a systematic perturbative expansion that's governed by interaction parameters like coupling constants. So usually in gravity, you make then an expansion in powers of g Newton. And then you associate, to make your life easy, then you associate, you write down a set of Feynman rules, and then you associate with various kind of algebraic pieces that appear in this expansion of your path integral of e to the is. You associate those with graphical elements, vertices, propagators, etc., that enable you then to systematically, order by order, figure out what the contributions are to quantum amplitudes of given processes, say with given in and out states. Yes, at a given order in your coupling constant. So that will get you to deriving a set of Feynman rules, and which enable you to compute contributions to amplitudes, order by order in perturbation theory. Now this is very schematic. The way I'm phrasing it here. I want to spend the rest of today spelling out some of the difficulties that you meet in the case of gravity, and I'll also, as part of the process, I'll write down at least a few elements of Feynman diagrams for perturbative gravity. Yes?
And here have this horrible problem with the measure being very hard to define, even in the free case.
No, not in the free case.
Why not?
What part of the measure? Well, I'll get to this because I give you some more details, and then you can, for the perturbative case, what it looks like there, and then you can ask. Of course, there are difficulties that appear, but they certainly can be overcome at the level of just constructing and writing down this path integral in a reasonably straightforward manner in the perturbative theory. Now, what I'll do for the time being and for the discussion of the perturbative path integral, I'll be setting lambda equal to 0 from now on. For the rest of the discussion today, now, only, of course, when lambda is vanishing, is Minkowski space a solution to the source 3 Einstein equations. If I have a non-trivial cosmological constant, then constantly curved spaces, I mean de Sitter or anti-de Sitter space, depending on the sign of lambda, would be the easiest solutions, the most symmetric solutions. So I'm interested in the situation where I'm working on a Minkowskian background, which is then also the solution, a solution to the equations. Now, what does the action explicitly become in this case? It's S equal to 1 over 16 pi G Newton, 4-dimensional integral, square root of the absolute value of the determinant of G mu nu times the Ricci scalar. And I hope I don't have to, do I have to explain what the Ricci scalar is? I hope that's familiar, sufficiently familiar from your GR course. So that, of course, contains up to second derivatives of the metric. Now, if I express it, of course, now I want to put myself in the simpler situation where I'm expanding everything into powers of f. So f was my linearized field, f mu nu. And I can now write schematically what this R is going to be. The lowest order terms will be of the character del f, and all higher order terms. And so you always have two derivatives per order. So the next higher order term in f will be of the form f, del f, plus next term will be, quadratic in f, del f. And of course, this is extremely schematic because f was a tensorial object with two indices. So clearly, various combinations and contractions of indices will appear here. But this is just to give you, the gist of what's going to happen here. Now, in order to absorb this prefactor and then express the rest just as as straightforward functions of the f's and higher powers, let me redefine what I mean by the f. Let me introduce a new f tilde mu nu, which by definition is just a constant multiple, 1 divided by square root 16 pi gn, the old f mu nu. Okay, so that will obviously get rid of this there, and it will make my action assume the following form. So I have some space here. So S will be equal to d4x del f tilde, very schematically, plus. Now, of course, every f, the derivative terms, of course, multiplied into this prefactor here, will always give me the same contribution, del f tilde, and however, any prefactors of f or higher powers, they will now come along with powers of the square root in the following manner. Square root 16 pi gn, f tilde, and times del f tilde, plus, and here get some, again, the square root gn f tilde all squared del f tilde plus, etc. Again, just schematically. And now, of course, what is the free theory? Is just the integral over this first term here. First term, there are various first terms. Again, you get some combinations of index contractions. Let's see, I have my colored chalk here. Yeah?
I'm not sure, but shouldn't there be second order derivatives of f as well? Because we have derivatives of the connection.
Well, of course, not necessarily, not the way, well, there is certainly a way to write it exactly this way, of course, but then by partial derivatives, you can shuffle derivatives around. So, but this is certainly one way of writing it. So this would be, of course, S3. And anything higher is, well, S, and this piece is, of course, the Lagrangian density, the free part of the Lagrangian density, and this thing here is then L interact. And of course, I mean, it's, of course, schematically is exactly of the type, you know, you'd find in scalar field theory, right? Then you have, of course, just a quadratic term, and then higher order terms from interactions. Now, very, let me make one remark here. So now you see, you have now this series appearing in L interact, and you now see explicitly that square root of G appears with the relevant power n at the nth order contribution of this expansion. Yeah. So that makes it very clear that this is kind of the relevant parameter in which we are taking the perturbative expansion. Now, in units, in our units, this can be seen to be inversely proportional to the so-called the Planck mass. So the Planck mass is a unique quantity you can construct, again, from C, h bar, and g Newton, which has the units of mass, of course. And here is, I have said, of course, C and h bar to 1. Right? So, but just to show you what, if we are just working now in our usual conventions and work in terms of mass dimensions, which will be now useful, then this Gn itself has mass dimension -2, and the square root of it has just mass dimension -1. Okay. Now, this is our coupling constant, and of course it's small. Well, what does it mean? It's small. Of course, this is a dimension-full quantity, right? But it's small in the sense, you know, if I have a mass here and a mass there, then the gravitational force they exert on themselves, on each other, is very small. As you have already seen in previous considerations we made. Now, what more can I say about this expansion? So the expansion of the Einstein action, it has infinitely many terms. And the reason for that is that the original Einstein-Hilbert action, either written in terms of G mu news or written in terms of F mu news, is not polynomial. Right? You get, for example, the square root of the determinant of G. And expanding that will immediately, you know, generate an infinite number of terms to you. So it doesn't just break off after a finite number of terms already at this stage. Now, what one does next, of course, the first kind of element in every such perturbative expansion is to understand and write down what the propagator of the theory is. So, of course, by that I mean to start with the free propagator. So, what is it? What do you do when someone hands you a theory in the form of an action or a Lagrangian? How do you determine its propagator? Now, the answer should be familiar already from what you've learned in QFT. And let me just remind you how it goes, say, in QED. Let me just look at the kind of the photon part. I mean, let me not couple any fermions. So then the action, just for the photon field, is of the form -1/4 d for x f mu nu f mu nu. And the basic field is, of course, the A field, of which this is a curvature. So the gauge potential, A mu. And what you do in order to extract the propagator from this, you write this in a form that is field, photon field, a quadratic, well, an operator times another photon field. So you bring it exactly for the variables you will see here in the that are relevant for this problem, involving also partial integration. You bring it to the form d for x, a mu, that is the elementary photon field, some matrix, including, of course, differential operators, mu nu times a nu. So that's the elementary field, and this is the form you bring it into. What you then have to do is to look at this operator and invert it. And then you get the propagator. Then you have the propagator of the theory. And what we need to do for gravity is do exactly the same, where now instead of the a mu, we have our little f mu nus. Right? So we just have to look at the action and just by algebraic manipulation bring it to the form f, some operator f. And then that operator we have to invert, and we'll see we'll meet related difficulties to what one finds if one wants to execute this program for QED, which has to do, again, with the presence of a gauge symmetry. So let me write down what the relevant Lagrangian density is for gravity. Fp here stands for Fierz-Pauli. So they first came up with this action for linearized gravity. So this is a Fierz-Pauli Lagrangian. Now, what does it look like? It's quadratic in the f's, the derivatives of the f's, f mu nu del lambda f mu nu minus 1/2 del lambda f mu mu trace, that is del lambda upstairs f nu nu minus del lambda f mu nu del mu f lambda nu plus del lambda f lambda mu del mu f nu nu. Okay, so that's characteristic for gravity. Your arm hurts just from writing down this Lagrangian. And you see an answer to who asked the question before. So this is exactly, it just has kind of it's quadratic in the first derivatives of f. Now, again, by doing suitable partial integrations, you can bring that into a form, which is f rho sigma, m rho sigma mu nu, f mu nu. And it's clear, of course, that the index structure has to be more complicated, just taking into account that the fields are now two tensors and no longer just vectorial quantities. Yeah?
So is that what's called Lagrangian function of that Lagrangian?
Yes, it's exactly this free. There's the free part.
Oh, the free part.
It's just the free part. And you can, of course, in principle, just derive it by sticking the linearized ansatz into the full action. Now, what happens is, of course, unfortunately, now our task would be to invert this quantity, this differential operator, with these many indices. Unfortunately, it turns out you cannot invert it because it has 0 eigenvectors. Right? And of course, this is exactly what happened also for the case of QED. And for a related reason, which I already mentioned various times, namely there is a gauge invariance. So M, unfortunately, is not invertible. It has a zero mode. Now, are we stuck here? No, we are not stuck, but of course we have to deal with the problem, and there's also nothing wrong with the physics, but it really, again, brings us back to the point that these F mu nus, if I think of them as kind of arbitrary two tensors, they're over-complete, so they still carry gauge redundance. Now, one way of dealing with it here is to add another term to the Lagrangian, which, well, in this case, breaks the U1 invariance this theory has. So this has a local U1 invariance under which these fields transform, these A mu fields. Okay. Now, by adding another term, you break this explicitly, and you can show it doesn't affect the physics in the end, but it makes as a nice, well, it has a nice property that it makes the propagator invertible, or rather that matrix M invertible. Now, what it was for, so one way of going about it in gravity is do exactly the same thing, namely add a so-called gauge fixing term now, which has a functional form curly F mu downstairs, curly F mu upstairs, to this Fierz-Pauli Lagrangian, where, of course, you should recall what this is, because I think I had it on the blackboard maybe a couple of days ago. When we're talking about gauge conditions, this is exactly the expression that appeared in the harmonic gauge condition. Del nu F mu nu minus 1/2 del mu F nu nu. And with this prescription, then kind of adding terms that contribute then to this matrix M coming from this F squared, curly F squared term, one finds for M how this differential operator becomes now let me call this M tilde, because I've added this term there now, rho sigma mu nu. It becomes minus eta rho mu, eta sigma nu, plus 1/2 eta rho sigma eta mu nu times del squared. And this happens to be invertible, which is invertible. And it really should remind you of the same procedure that works here, when, here for the case here, you add an F squared term, where F is essentially del mu A mu. So then all I said now for what holds for the gravity field works for the photon field also. just with a few more indices. Now, of course, this is not, I haven't derived anything for you. I have in part appealed to your being familiar with the logic of how this comes about in QED for the electromagnetic field. There is a proper way of formalizing this, which I just briefly mentioned only by name. That goes by the name of Fadeev and Popov. And it's just a prescription, that works for kind of a general path integral with a gauge symmetry. Now, what is the problem now from the point of view of the path integral to have this gauge redundancy in there? Well, the problem is that these gauge directions usually give you infinite contributions, divergent contributions to the path integral. Because especially here, I mean, we are working with a gauge group that is, of course, is not compact. Anyway, it's a functional gauge group. So if you integrate over these gauge directions, that immediately gives you, well, an infinite contribution, which, however, you would like to get rid of, because on top of everything, it doesn't contain any physical interesting information. It just counts all the redundancy. So it just means you're overcounting, the ever same physical configurations. So what kind of the Fadeev-Popov trick is, roughly speaking, it inserts a kind of a delta function into the path integral, which restricts you to some restricted to a submanifold of your configuration space, the configuration space you're integrating over. The way it's usually phrased is that what you're doing, you're inserting a factor 1 in the path integral, and this you rewrite in a somewhat non-trivial way as a product of various components. So the first one here is kind of what's called the Fadeev-Popov determinant. You see, it refers to a gauge fixing condition already, this curly F. Then you get an integration over the gauge group. So I'm using now this G, but this is not the G mu nu. Okay, so this is an integral over the gauge group. So these are exactly the redundant, the unphysical gauge degrees of freedom. And what it does here, it inserts, as I said, a delta function associated, now in this case, with a finite bunch of such gauge conditions, F mu. So the gauge condition consists in setting these 4 curly Fs, F mu's to 0. So that's just associated delta function I'm inserting in the path integral. And the statement is that this has been chosen exactly such, that this is indeed 1. This whole thing is 1. Where, of course, I'm hiding infinities. I mean, that's infinite. So I somewhere am canceling kind of this infinity. Yeah. But this is, roughly speaking, what happens. So this is the Fadeev-Popov determinant. And this is needed. At first, I mean, people kind of overlooked this, that this should be there. So, of course, inserting a delta function, that's kind of the obvious thing to do. But I already explained to you, well, why a gauge choice has to involve more than that. Because I told you, well, what I have to take care of is a Jacobian of the transformation on my configuration space that splits up, say, the F mu nu's into kind of the gauge part that satisfies these constraints, plus the rest, which I'm thinking of as physical. And this split, well, is implemented by certain coordinate transformation, and the Jacobian of that coordinate transformation turns out to be exactly this Fadeev-Popov determinant. And in order to make this linearized gravity theory unitary, it emerges, well, you must take this into account. Yes?
In this case, or?
It's a linearized diffeomorphisms. So I think we had the transformation law. I mean, I think we had it on the blackboard as a function of epsilons. Yeah, so that's what it is, because it's infinite dimensional. Is it a GL4? Linearized. Huh? Well, it's something slightly. A copy of that in every point. Well, no, it's a linearized diffeomorphism. So it is something slightly different. So it's not arbitrary. It doesn't boil down to arbitrary GLs. Yes?
Why do you take the linearized diffeomorphisms and not the full set of diffeomorphisms?
Yeah, well, this is what kind of the diffeomorphisms boil down to when I consider the linearized approximation of the theory.
Linearize both in the...
Yes. Kind of, it matches. So if I was just going to write down kind of the transformation law, right, minus del mu epsilon mu minus del mu epsilon mu, then in order for this to make sense, but the epsilons are of the same order as the f minus. Yeah, but it's not deeper than this. So here I just state this. I mean, so this functional determinant is really needed in gravity to make this linearized theory unitary. And that is an observation. It was first made by Bryce DeWitt back in 19. No, it was observed. It's written here by Feynman in 1964, and the problem was solved by DeWitt in the same year. Now, there are many more things one can say about this, and also this won't do very much for you if you haven't worked with this yourself, say also in a somewhat simpler gauge theory. But this is what the story is. What I briefly do now, which I promised to you when we started talking about perturbative path integrals. Well, now we've exhibited a differential operator that can be inverted. Now, what is a propagator in that harmonic gauge? And in the corresponding Feynman diagrams, this is the propagator associated with a wiggly line like that, with a 4 momentum label K. Of course, I'm talking about momentum space, the Feynman rules. And I have to keep track of a bunch of indices, mu1, mu1 on this side, and mu2 on that side. And this corresponds to an algebraic expression, of course, of the same index structure. I have one bi-index mu1, semicolon, and then another pair mu2. Everything depends on K. That's the propagator in momentum space. And then I just get a bunch. This is an expression that's quadratic in the entries of the Minkowski metric with various permutations. Here, mu1, mu2, eta mu1, mu2, plus eta mu1, mu2, eta mu1, mu2, minus eta mu1, mu1, eta mu2, mu2. and of course accompanied by usual denominator k squared minus I epsilon prescription. Okay, now you see you start calculating amplitudes, and your elementary building blocks are the propagator and vertices incorporating interactions of the gravitons, self-interactions. And since this is just not a linear theory, you find self-interactions at any order. Right? So to start with, the simplest one is a 3 graviton vertex. Graviton vertex. And again, the explicit form of that depends on the gauge chosen. So now I have written down everything in harmonic gauge. So the same holds true for this vertex expression. In harmonic gauge. Now, see, this of course corresponds to a threefold intersection. 3 gravitons meeting associated with 4 momenta K1, K2, and K3, and index pairs mu1, mu1, mu2, mu2, mu3, mu3. Okay, now what is it? Let me call this capital V for vertex. Now, many indices, mu nu 6 in total, pair mu1, mu1, mu2, mu2, and sorry, no commas here, mu3, mu3, and of course, depending on the 3 incoming momenta, K1 to K3. And now here we go. K1, scalar product K2. And now we have a bunch of etas, eta mu1, mu1, eta mu2, mu2, eta mu3, mu3, plus K1, mu3, K2, mu3, eta mu1, mu2, eta mu1, mu2, plus. Now, I have only like 3.5 minutes. Now, there are more than 100 terms to be added here. More than 100, okay? So you forgive me for not writing them all out. Of course, what you see that happens, right, of course, there are only, well, so many things, well, quite a few things, you can write down which have this index structure. And the only thing you have available on the right-hand side are etas and k's. But of course, there are quite a few ways of combining them to get a kind of a 6-index object. So you can make a general ansatz, and then you can fix all the coefficients on the right-hand side. And that's a heck of a lot of work. And again, I think the first person to work this out, well, it's not. That's who it was. So plus more than 100 other terms of this kind. And the person who first did this work and worked out this vertex was again de Witt. He had a lot of stamina. Even when I only met him once or twice when I was a young student, and he was quite old by then, but he still had a lot of that stamina, obviously. Okay, now note that here, well, vertices they're not just constant, but they're momentum dependent. Here, I mean, for the very simplest field theories, this doesn't happen, but this is clearly the case here. And of course, you must also think that it's just, one vertex. There are, of course, many, many, many more vertices of higher order. And I can't even imagine thinking how many terms those have. But this is exactly what you have to deal with if you want to compute, well, amplitudes, graviton scattering. So that keeps you busy. Yes?
Do we expect factors of square root of Gn here? Or is that in a different...
Yes. Yes, there should be. You're completely right. That should be somewhere. That should be somewhere here. It's not written here. So I imagine that's the square root of Gn in front of this, yeah. Yes, exactly, because it just comes from the cubic term of that expansion. Yes. That clearly belongs here. Okay, now, the question arises, it's of course an independent statement that this looks just terribly complicated. Right? But is there anything wrong with that in principle? Well, also that perhaps not, but what is wrong in principle that if you keep doing this, unfortunately you're unable in the end to extract sensible results, well, because the theory turns out to be, as one says, non-renormalizable perturbatively. That is, you cannot, in a systematic way, renormalize or redefine the coupling constants, the bare coupling constants of your original theory in such a way that the divergences which you now start meeting in when you compute loop diagrams, etc., are absorbed, and what remains is finite. So gravity is just not a theory of that type. So one could say one is unlucky. At least that is a property that emerges from this perturbative expansion. So could I have anticipated already at an earlier stage that I might have a problem? And the answer is yes. And the answer has crucially to do with what I was writing here at the top about the dimensionality, the mass dimension of the coupling constant. So this is a negative mass dimension, and as it happens, this is a characteristic feature of theories with nasty properties of their perturbative series, and of course, in particular, non-renormalizability. So here again is my coupling. Let me just briefly make the argument, the short argument, for why we might have anticipated running into trouble. So here is my Gn, G Newton. And now let me use these square brackets to indicate mass dimension. So this is -2. Now imagine I now do an amplitude, I attempt an amplitude calculation. What I always can do at an intermediate stage, and what I usually have to do when divergences are present, I introduce a cutoff. So I cut off the integrals at some fixed high momentum, or momentum squared. That hopefully makes then the integral finite. And then I study, as I do, usually in field theory, systematically, the dependence or the leading divergence and how I might remove the leading divergence. So a momentum cutoff is introduced, which I call capital lambda, and it should be much bigger than kind of relevant physical energies present I'm interested in the system. Now imagine I'm after computing some amplitude, curly m, then I get a zeroth order term now I'm interested in an expansion as a function of the coupling, a power expansion, in the coupling constant Gn. Now, how will this start out? Well, I have some lowest order, and then I have a first order proportional to Gn. But of course, this is the dimensionless quantity. So which dependence must it necessarily have as a function of lambda, kind of the cutoff integral? Well, it must go like lambda squared, obviously. So then this whole thing is dimensionless. That, of course, has dimensions of a mass, of an energy, right? So it must go like that. Higher orders, Gn squared, must be accompanied by corresponding higher orders in this lambda cutoff. And you can already see that this spells disaster, these higher order terms, because of course I want to send lambda to infinity. And what I see here is that if I really do this, then the contributions in my perturbative series will blow up the higher I am in this perturbative series. And the immediate origin is clearly the dimensionality, the mass dimension of the coupling constant. So you already see that you're potentially in trouble just from this dimensional argument. And the divergences kind of seem to get worse the further I go along in this power series. And of course, what I'd love to do, of course, is this should break off or converge in the best of cases. Now, one might be lucky that although this dimensional argument is completely correct, it might be so that the coefficient which appear now at a given order of the coupling constant conspire to sum up to 0. Right? There are, of course, typically many diagrams contributing, and of course, looking at this, with a lot of work, you'll have to find them all and add them all up, and you just might be lucky that the prefactors in a specific episode, they just didn't happen to be 0. And then, of course, everything's hunky-dory. But with a lot of work, well, for very simple, the lowest order calculations were made. These calculations were made. And one finds, well, it certainly finds one surprise, that if you just look at pure gravity, the miracle happens at the order of one loop. So there is a potential divergence there, but it cancels. So pure gravity, or quantum gravity, perturbative quantum gravity, is one loop finite on shell. Taking into account equations of motion, that is. And that's a famous result by 't Hooft and Feldman. From 1974, so not all that long ago. Unfortunately, the miracle doesn't continue at the next order. So at 2-loop order, the relevant coefficients can be shown not to vanish. So this is no longer true at 2 loops for pure gravity. And it's also no longer true if, say, I couple scalar matter. So this is the statement I'm making here for pure gravity. No longer true. And that is also a famous result by Gorov and Zagnotti from 86. And you can already see, right, it took quite some time to get to here. And of course, what plays a role is really how efficiently can one go about doing these computations? Can one be clever about them? So there's always another name associated with this, that of Anton van de Ven, who redid the calculation in a somewhat more clever way later, but also, of course, this is a highly non-trivial affair and reproduced this answer. Now, this result had been anticipated. So people were suspecting that it would be so, but this kind of, in a way, closes the door to having perturbative quantum gravity, a valid theory that will describe gravitational physics at arbitrary energy scales. If you're content with working for a lower range of energies up to some lambda, where this is a good, the perturbation series to some order is a good approximation, that's fine. But if you're interested in a series that should be valid kind of at arbitrarily high energy scales, including, of course, the Planck scale, where this wildly diverges, then this is not good enough. And one has to think of something else. But we're not going to do this today, but starting next week.